Very good afternoon to one and all, and good morning to Professor Sir John Pendry, who has kindly agreed to deliver this special public lecture on the topic Metamaterials Open New Horizons in Electromagnetism. This particular special public lecture is part of an year-long series of webinars which the National Academy of Sciences India Delhi chapter and the Upadhyaya College, University of Delhi, jointly organized during this pandemic for the benefit of all the students, research scholars, and faculty members who have been devoid of an opportunity to visit the classes in the physical mode. Professor Sir John Pendry is a fellow of the Royal Society and is associated with Department of Physics, Imperial College London. So before inviting Professor Pendry, I would like to briefly introduce him to the attendees. He's the chair in theoretical solid-state physics at Imperial College London, a position that he has held since 1981. A student of the University of Cambridge, he started his research career with a PhD in physics in 1969, when he became a fellow of the Downing College. He left his native England for a research position at Bell Labs in 1972-73. He returned to Cambridge after joining the Daresbury Laboratory in 1975 and eventually Imperial College London, where he has served as head of the physics department and as principal for the Faculty of Physical Sciences. His early research interest focused on the electronic properties of surfaces. He developed theories that enabled the practical use of techniques for the study of the properties of surfaces, such as low-energy electron diffraction and angle-resolved photoemission spectroscopy. In 1992, he started the study of the interaction of light and matter that would lead to the design of metamaterials with negative refractive index. In the year 2000, he then predicted that such metamaterials can focus light with unlimited resolution, proposing the concept of a perfect lens. In the early 2000s, he proposed the idea of an invisibility cloak that would hide objects from electromagnetic radiations. The proposal was taken more seriously than he thought and led to the experimental realization of such cloaking at microwave or visible wavelengths. He has won several awards, including the Dirac Medal in 1996, the Royal Medal in 2006, the UNESCO Niels Bohr Gold Medal in 2009, and the Isaac Newton Medal in 2013. He was elected Fellow of the Royal Society and Fellow of the Institute of Physics in 1984, and in 2004 was knighted in the British Honours for his services to science. In 2013, he was made the Foreign Associate of the US National Academy of Sciences. With these words, I now invite Professor Sir John Pendry to kindly share his screen to deliver his talk.
Thank you, Manoj. Can you see my screen now?
No? So you have to share the screen again.
Yeah, I'm pressing this button. And yeah, okay, I got it. So we share. Now can you see my screen?
Yes.
Good. Okay, I'll then go to presentation mode. And that should be full screen. Good. Okay. Well, thank you very much for inviting me to this special series of lectures honoring your 75th anniversary of independence. It's a privilege to be speaking on this occasion. I want to tell you about these things called metamaterials, which have been around for some time, but are now making inroads into devices and practical applications. So it's a rich story, and I'm going to begin at the beginning with its rather theoretical origins. So what is a metamaterial? A metamaterial is something which gives access to material properties never before available. And unlike photonic materials, these materials do behave just in the same way as ordinary materials do with respect to Maxwell's equations. They can be described by permittivity and impermeability. And this simplifies the design process if you're going to use them. Alongside metamaterials, has been developed a paradigm of design called transformation optics. And I'm going to be talking about that as well, because it's central to some of the things I have to explain to you. As well as having these novel properties, internal to themselves, they can have intense concentrations of electromagnetic energy. And this enables nonlinear properties to be enabled at relatively modest powers, so you can exploit it for switching, time reversal, for wave mixing, and so on. So a little bit more detail about how they're made. So in conventional materials, their properties derive from the constituent atoms of molecules, and its response to an electrical magnetic field is given by the average over many, many billions, indeed, of molecules within, say, the wavelength of light. And metamaterials recognize that these small entities, molecules, don't have to be chemical molecules. They can be entities which are very small, but nevertheless are large enough that you can manufacture them. So these artificial molecules are the entities which control how a metamaterial will behave. And so in designing a metamaterial, you have to use real materials, of course, so chemistry comes into it. But in addition to chemistry, you have this, this option of varying the geometry. I'll give you a very simple example of a metamaterial with which you might be familiar. If you've seen an old-fashioned photographic negative, then from the era of black and white film, then the black in that negative is silver. And it's not silver, as you know, a piece of silver in a mirror, which is highly reflective, of course. It's silver which has been deposited in the form of very, very small nanoparticles. And that change in the silver's structure means that its optical properties are radically altered from being an excellent reflector to a really excellent absorber of radiation. So metamaterials derive their properties from the geometry of their constituent units, and they can be engineered as we please. Here is an instance of the first metamaterial that we made after we had this idea of metamaterials. I should say that the concept of metamaterials spans more or less a whole range of electromagnetism up to almost to the UV. It is easiest to employ at radar frequencies because our wavelength is long enough that this condition that the little units, little molecules, if you like, should be smaller than the wavelength is more easily realized. For example, this structure here, the little rings you see, which I'll explain in a moment, are only less than a centimeter across. And actually it's made on a perfectly conventional circuit board. Later, I shall show you examples where the structure is operating at near visible are much smaller and therefore more expensive to make. This particular structure was designed to give magnetism without using any magnetic materials. Now, in RF, in radar applications, which this company Marconi was involved in at the time, you often need materials with a magnetic response, and the natural materials available at radar wavelengths are very, very limited and are lossy. So we set about trying to make something with a magnetic response, but wasn't made of magnetic materials. And you can see how this works, because if you insert a magnetic field normal to the plane of this ring, it's going to induce a current flowing around the ring. And that current will in turn generate a magnetic field along the axis of the inserted field. And so you get a a magnetic response just from shaping a piece of copper. But there's more to this structure than just being a ring, because if you notice here, the ring is split. These are split rings. So the current can't flow round the ring unless it jumps the capacitance across the ends of the rings. And that's the idea, that you have built essentially a little electrical circuit here of a ring, which is essentially an inductor. And it can only operate because of the capacitance between the two rings. And so you have inductor, capacitor, you have a resonant circuit. And so in addition to providing magnetism without magnets, this also has another unusual property as a consequence of the resonance. Now, resonators have the property that their response is a function of frequency, and obviously, if the frequency of the radiation is equal to the resonant frequency, then you get a very drastic response. Below the resonant frequency, the response of the ring is in the direction of the field applied. But if you tune the frequency of the magnetic field above the resonant frequency, then the response flips and it changes its sign. So you have created here something which can do negative permeability. And unknown to ourselves, that was something that was missing in nature. There were hardly any materials with negative permeability, a negative magnetic response. But here we have one which at certain frequencies does. And that has been quite an important ingredient in the story of metamaterials, because what really kicked off interest in them was this subject of negative refraction. Now, there's a backstory here, which is that a Russian scientist many years ago, in 1967, 68, wrote a paper saying that if you could make a material with a negative refractive index, then there are lots of very, very strange things followed from that. And I'll talk about some of them. His name was Veselago, and he gave us prescription for making a material with a negative refractive index. And the prescription was that the electrical and the magnetic response should both be negative. And a lot of interest was generated by his paper. But despite searching and searching, although people could find materials with a negative electrical response, there was no results for a negative magnetic response, at least at the same frequency at which the electrical response was negative. So the idea, eventually, people lost interest in it because you couldn't do it. And that's a bit of a lesson for all of us, we theorists, that if you can't persuade an experimentalist to realize your ideas, then your idea will probably gather dust on a shelf. Now, this is the first realization of a negative refractive index structure. It was made by David Smith when he was at UCSD in California. And it's an adaptation of our split rings. They're square rings, actually. And these give you a negative magnetic response. But in addition, on the other side of the circuit, but you can just see it as a shadow here, there's a wire. And that wire is an electrical resonator. And that resonator is tuned so that you also have a negative electrical response. And that gave the first material with a negative refractive index. And that really kickstarted a lot of interest in the field, being able to realize these most exotic properties. I promised to show a material which had a negative refractive index, a negative response, near visible. And here's a material which has a negative response in the communications region of the spectrum, the near infrared. And it's a so-called fishnet structure, and it consists of 30 nanometer thick layers of silver into space with an insulator in the form of magnesium fluoride. And is structured with holes in it. And there's an electron micrograph of the structure. Here's the scale, which is 1 micrometer. And you see that the scale is just less than a micron. It has this property of negative refractive index in the near visible. It's made by the Zhang group in Berkeley, California. The Zhang group has been very central to the story of metamaterials. And since those early experiments and theories, the subject has grown. We can do giant pyromagnetism for DC fields. It's been turned up in magnetic resonance imaging to design safe pickup coils using metamaterials. It's now a prominent feature in the 5G network, in 5G cell phones, and even more prominent in the 6G. I was in the Huawei laboratories 3 years ago, and they have the most advanced 5G technology, I believe, and they were very enthusiastic about the role which metamaterials play in that technology. It's been used at terahertz frequencies. Capasso at Harvard, who was the inventor of the quantum cascade laser, has made metamaterial structures to enhance their efficiencies. It's been made to control thermal radiation with broadband absorbers, and in the visible for enhanced nonlinear phenomena, single molecule detection, chirality, and so on. Not confined to electricity and magnetism, it's also now being introduced in acoustics, and I'll have a slide later on about some applications of that, applications to domestic environment of soundproofing and to stealth technology. Even in mechanics, you can make metamaterials with novel mechanical properties, things like a negative Poisson's ratio. A guy called Vincenzo Vitelli, who used to be at Leiden when I met him, and I think now he's in Canada, is an expert in these topics. So a little bit more about this negative refraction. If you look at Maxwell's equations, and here is the time-varying electric field, then the wave vector defines how the light propagates. And Maxwell's equations tell you that the wave vector is related to the electrical and magnetic response by this formula here, which dictates the refractive index. Now you can see from that formula, if either one of these, epsilon or mu, is negative, then that assumes that the wave vector is imaginary, and essentially the material is opaque because waves decay exponentially in space. However, if both these are negative, then you're faced with a positive number again, and the material is transparent again. And you may think that's the end of the story. And it is transparent, but it's very, very different. I like this quadrant diagram here, where epsilon is along this axis and mu the other. And when they're both positive, they're transparent. And when they're both negative, they're also transparent, but they're different. And you have this phenomenon of a negative refractive index. Now, the recipe is that both epsilon mu are negative. And Victor Veselago showed that if epsilon mu are both negative, then this formula, the refractive index, we have to choose the minus sign. In a very simplistic way of putting it, you can say that since what you have here is -1 squared, then when you take the square root of it, then that has to be a minus sign. I don't think many mathematicians will accept that answer. There are more subtle arguments to do with causality. However, we'll have to suffice for a short lecture. Negative refractive index. The traditional way of defining negative refractive index is by refraction at a surface, Snell's law, if you like. So the refractive index is the ratio of the sine of these two angles. And if we define a normal material to have a positive refractive index, then θ2 will be off in this direction in the material. But when you have a negative refractive index, the light bends back on itself. So theta, by this definition, θ2 is negative, and so you get this negative refractive index. But immediately with this most simple of diagrams, you can see why a negative refractive index actually faces us with some paradoxes. And the paradox in this instance is that there's a very, very strong conservation law, which results not so much from physics as mathematics, that if a wave is incident on a translationally invariant surface, a flat surface, then the parallel component of its wave vector must be conserved across the interface. And you can see on this left-hand side that if I take this wave vector here and project it onto this surface, there is no way that if the wave vector is traveling in this direction, which is the direction of energy flow, if the wave vector is also in this direction, then there's no way you could match something which is positive with something which is negative. And so the solution you're forced to, the conclusion you're forced to, is that the direction of the energy flow, the pointing vector, if you like, and the wave vector are decoupled, and they head in opposite directions. So you have to have this situation. There is no choice. You must have the wave vector inside the material, which is the negative refractive index, pointing in the opposite direction to the flow of rays. And that's the first part of one of many paradoxes. How does this have consequences? Well, here's that picture once more, and we can see some of the strange things that might happen by considering a wave packet. So the outline of the wave packet here in red, the direction that travels is dictated by the group velocity, and that is the direction of how the energy flows. It flows with the wave packet, obviously, because it takes its contents with it. But look inside the wave packet, and we have the waves themselves, and they're traveling in the opposite direction. So just as the profile moves in this direction, these wriggling waves are headed in the other direction. They start here and they wriggle through and go out of the back of the material. And that's a little bit, it's never been observed for light because negative refractive index has never been observed before metamaterials. It has been observed in some other forms of waves, like water waves, I believe. And I can compare the phase velocity a little bit to like a clock. And in this wave packet, you see that the waves going backwards are a little bit like a clock going backwards. And I'll come back to that later. So there are connections between time reversal and negative refraction. It's not the same, but there are connections to do with clocks going backwards. A little bit more about negative refractive index and focusing. One of the things Veselago pointed out was that negative refraction can focus without having a curved surface. And that's fairly obvious because if this ray hits a surface and is bent back on itself, then this ray is going to cross the axis a second time. And indeed, it's going to cross the axis a third time. So you get two foci when light enters this negative refracting slab. And Veselago pointed that out in 1968, but of course it was never realized because you couldn't make the stuff. And that also is something which is really weird about negative refraction, because if you look at this little diagram here, you see that if you have an object inside a negative refractive material, then you will, observing it from the outside, you will see that point here. So if you have a fish swimming in your negative refractive index pond, then you will see that fish swimming about in air above the pond. Another really strange thing. Now, you remember, you can understand this by, maybe at school you learned another formula for the refractive index, which is the real depth of an object divided by the apparent depth. And if the real depth is positive, and then the apparent depth must be negative. So you have to see something above the surface. Now, before I can explain all this, I need to do a bit of theory. And that theory is transformation optics. And it's been developed in parallel with the metamaterials story. The old optics, which we use all the time still, is built on the ray approximation. It thinks of light as a stream of particles, and refraction takes place at discrete surfaces, as I show here, and it works with limited material properties. Now, you might ask why we still talk about rays and so on and so forth, and despite the fact that we have Maxwell's equations, which have described the full story of light as a wave, refraction, reflection, diffraction, and so on and so forth. And the reason is that it provides a very, very simple picture so that you can see what a particular experimental setup might do. You can see in your mind's eye what it might do. And what it might do if you change some of the parameters. So it's an excellent design tool, and is still used in the design of lenses. But in modern applications of electromagnetism, you often work in terms of dimensions of structures which are much less than the wavelength of light, and then the array has no meaningful concept there. And so you can't apply Snell's law to subwavelength optics. And if we are in this regime, actually we do have some quantities which you can still be visualized. And these are the fields, the electric field D and B. These are lines of force, if you like, electric and magnetic, and they can be manipulated and visualized just as you can with rays. So if we can find some rules for manipulating electric and magnetic field lines, then we can have a tool for subwavelength optics and exploit the potential metamaterials. And that's what transformation optics is about. It's manipulating D and B. Now, this gentleman needs no introduction, I assume. And one of the many astounding things he did was the general theory of relativity. And in Newtonian times, when people talked about a force, they talked about action at a distance, action between two charged particles acting at a distance, but the force directed along the line separating the two entities. And that's the simplest way to describe that force. But often the simplest way is not the most useful way, and it's Occam's razor says you should choose the simplest way, but you needn't. And sometimes if you have a little bit more complicated way of describing it, it gives new insight. And that's what Faraday did. Michael Faraday was a man who discovered the laws of magnetic induction. And Faraday thought about the force between two magnetic poles, not in terms of action at a distance. What Faraday said was, there is actually a field, something he called a field, surrounding a North Pole and a South Pole. And this intermediate concept of a field is what transfers the force. So a North Pole would have a field surrounding it, which would be there whether or not the field was exerting a force on a South Pole. And this concept of a field is absolutely central to modern physics. Field theory is what the advanced theories of particles is based on, the Standard Model, and so on and so forth. Modern physics wouldn't be the same without fields. Interestingly enough, the concept of a field was introduced by Faraday, the son of a blacksmith who had no formal education in mathematics. It's another paradox we come. And the concept of a field was what Maxwell invoked to explain gravity. And people in Newton's time said gravity was like action at a distance, the gravitational field acting between two massive objects. But Einstein said, oh, no, there's a field. And that field was the geometry of space. And before that, people had thought about space as empty. They ran out of words to describe something which was nothing. Space, vacuum, void, and so on and so forth. All these are different English words for trying to describe nothing. But Einstein said space isn't nothing, it's a material, just like other materials. It's defined by its geometry, and its geometry can be changed. Its geometry can be changed by, excuse me, by a massive object, which actually bends and shapes the space. That was a fairly radical concept. And one consequence was that if you wrote Maxwell's equations using this funny space that Einstein thought up of a curved space, then you found you could actually rewrite Maxwell's equations in this funny space, and they still look like Maxwell's equations, but something appears in them which wasn't there before, and that's a refractive index. So a curved space appears to have a refractive index. And in fact, that observation created one of the cornerstones of the experimental confirmation of the general theory of relativity. Eddington, Arthur Stanley Eddington in 1919 suggested that you could actually observe the bending of starlight as it passes close by to the sun, and arguing that because the sun was surrounded by slightly bent geometry, even the sun doesn't bend space very much, slightly bent geometry, it should act like a lens and deviate the course of light. Now, you can only look very close to the sun if there's an eclipse. So he went off to, I think, somewhere in New Guinea, and he made an observation which actually confirmed the prediction of Maxwell's theory to the deviation of starlight. And that theory solved the problem which had been around for some time after Maxwell's equations. And the question, Maxwell's equations revealed the nature of light, that they were waves, they were electromagnetic waves. But the question remained of what were they waves in? So a water wave is a displacement of water. It's the water that moves. A sound wave is the displacement of air, and so on. What is moving when light propagates? And that was a problem. What was the medium that carried light? And now with Einstein's concept that the space isn't empty, it's full of geometry, which can be changed, then the medium which is carrying light, people after that were perfectly happy that the medium was so-called empty space, which was actually full of this Einsteinian geometry. Now, more massive objects bend light a good deal more than that. This is a fun picture from the Hubble telescope of a gravitational lens. And what you see here is a very massive galaxy, a red galaxy, which is in the foreground of this picture. And behind it, there's a blue galaxy. And the light from the blue galaxy, far from being occluded by the red galaxy, actually is bent around. So you see this ring of light, which is being bent around, rather like the cloak I shall tell you about in a few minutes. Okay, so Einstein said that if you can bend space, you can bend light, you can bend the rays of light, and therefore you can bend the field lines of light. So we're going to exploit that, because what he also said was that in the case of light, you don't have to have a massive gravitational field. As far as light is concerned, a refractive index will do the job just fine. And that's useful because gravitational bending is not easy to come by. So here's the idea. We first stumbled across this where some ideas which were well known previously, actually, but in this context, Andrew Ward and I used it in 1996. And the idea is this, that if you take a ray of light or a field line, a magnetic one or electrical one, or anything that's conserved, in fact, and I've drawn some Cartesian coordinates here so that you can see how I'm distorting space. Now I'm going to distort space, and when you distort space, you actually drag the field lines with it. So this is a rubber space, according to Einstein, because you can distort it, but the field lines are embedded in the rubber. So when the rubber moves, so does the field line. And so it follows this curved trajectory here if you can bend space. Now, out of Einstein's equations, you can come to some expressions for how much you have to change the refractive index for this to happen and for it to be equivalent to a bent space. And here's the formula in terms of mathematical properties, such as the first derivative of the coordinate system. And using these equations, you can calculate what values of epsilon mu you need to bend the light in this direction. The same transformation applies both to epsilon and to mu. So that's where metamaterials come in, because if you're going to have this complicated three-dimensional or two-dimensional distortion of the refractive index, then obviously you need some fairly fancy materials to do this. And that's how metamaterials happen to help this story of changing lines of force as we wish. Not everybody can look at the coordinate transformation I've just shown you in the previous slides and visualize what's happening. So instead, I'm going to give you an intuitive picture of what might happen if you compress space. So I'm going to make the simplest compression of space. And here's a line of force, or it could be a ray of light, or a electrical magnetic line of force. And I'm going to squash the central region here. So now the ray goes in this direction here. And then I can ask what values of an epsilon mu would distort the path of a ray of light in that direction. And the answer is that if you compress along this axis, then along this axis, the permeability and the permittivity are decreased by the factor of compression. So you compress and you make epsilon mu smaller along this direction. In contrast, in this direction, normal to the compression, epsilon mu are increased by the inverse of the compression factor. So decrease, increase. And with that simple distortion, you can imagine that combining distortion in all three directions and maybe a rotation as well, you could in fact calculate what the local epsilon mu was for any distortion of coordinate system. So there is a visual picture that you can make of this. Now, we were fairly excited by this idea of being able to control fields almost at will, and we thought, well, maybe first order derivatives of coordinate transformations wouldn't catch much attention, even in physical review letters or science magazine, and certainly not to the general public. So we thought, what can we do that you couldn't do before you had this idea? And the idea came up of making something invisible. And as Manoj said in the introduction, the concept of invisibility was first a joke. You know, we thought people would laugh when we said it. They didn't as it happened. Now here's the challenge. So this isn't Harry Potter, who's the icon of youth today. This is Peter Pan. And some of you may know the story of Peter Pan, a little boy who never grew old. But one thing he did was to lose his shadow. And that's a secret, you see, because if you want to make Peter invisible, here he is, his statue in Kensington Gardens near my college. And if you just paint him black, then you can still know that he's there because he has a shadow if you see him against the bright background. And that's the real challenge of invisibility, to get rid of the shadow. And if you can do that, then Peter's gone and he's invisible. But how to do it? So we know that by changing the refractive index, you can change the direction of light. So suppose you were a busy research professor and you wanted to design a cloak. You knew in principle you could do this, direct light around. It hasn't got to go into the invisible region because you'd see something if it did. You've got to start it off in a certain direction and it must emerge in exactly the same direction. Otherwise you could see this distortion, and you must contain all this activity, all this cloaking within a finite volume surrounding the hidden region. So the busy professor says to his graduate student, okay, sit down, do a bit of ray tracing and come up with a distribution of the refractive index. And the student goes off, and after a bit of time, he feels this is really a tough challenge because you have to, he starts with this ray and he says, okay, I know how to steer this ray around, okay. And it goes to here, that's fine. So I fixed one ray. But now about a second ray coming in from a different direction. You've got to do the same for that. But your ray moves through the same stuff that you've already finely tuned for this ray here. So it's a self-consistency problem of enormous complexity, very, very difficult. However, transformation optics can solve the problem in one stroke, and here's how it's done. So I take some space, which is empty, a refractive index of 1, and I make a hole in the space. So I poke my finger in the space, thank you, Mr. Einstein, and I compress all this space here into an annulus. And I've created an empty space here, which doesn't even have a refractive index until I put something in there. And whatever is in there will remain hidden, as I'll explain in a moment, because you remember my rule when I explained that you could distort space. The rule was that when you distorted space, all the electrical activity and the magnetic activity moved with that rubber sheet. So if you have lines of force due to a ray of light going through here, then all those field lines are taken out of the central region and never enter this hidden region here. Also, another bonus is that if you don't move the rubber sheet, you don't move the lines of force. So all the lines of force everything outside is just as it was before you were tinkering around with them inside here. So you achieve your objective. Viewed externally, nothing's changed because you haven't distorted space out here. Inside, you have created a region which cannot be seen because no ray can access it. You've expelled every possible ray from this region here. And then if we go to our compression formula for the refractive index, the coordinate transformation here is very simple. There are several you could use. This is the simplest one. Then from this, you can derive the formula for what epsilon and mu must be inside here. You can even do it to cloak magnetic fields, and I'm a little bit short of time, so I'm going to skip over that. This is the first cloak that was designed by David Smith and myself and his group now at Duke University, and you can see these metamaterials changing their shape. This is a cloak to be put inside a two-dimensional waveguide, so it's a cylindrical cloak, and this is the hidden region, this is the cloak. And here are some simulations compared with experiment. So if you simulate with exact material properties, the radar waves, this is a cloak for radar waves, centimetric radiation, the radar waves pass through undistorted, and you can see that it's the image, the rays are undistorted by the wave fronts, which are parallel. And if you look at the experiment, well, yes, it's essentially doing what's happening here with the simulation. And the wave fronts are coming out straight. They are attenuated. So what you would see here is in fact a gray smudge, but you wouldn't see what was inside it because the rays are essentially excluded from the inside. So that was the first cloak, and it really attracted quite a lot of attention. And I want to move on from the cloak to the Vesilago lens, because something else was realized. I realized something else about the Vesilago lens way back. As soon as I heard about it, I thought, well, that's really intriguing. There's something very strange about this lens. And after some thinking, what I realized was that this lens doesn't just focus rays. Now, I should explain that an ordinary lens, such as you have in a microscope, has limitations due to the finite wavelength of light. And Abbe, a 19th century scientist, showed that with an ordinary lens, you can't see anything which is smaller than about a half or a quarter of the wavelength of light. And that's a huge limitation in a microscopy. Biologists, their tool of choice is the optical microscope, and they use it to peer at cells and biological structures. And the cell is just getting interesting at the length scale of the wavelength of light. So the really interesting things they can't see, and there'll be massive efforts to do sub-wavelength imaging. But actually, if you could make this Vesilago lens, it would make an image which is perfect in spite of the Abbe's law. It will focus all the radiation near and far field. Now, there is a way to explain this. Isn't the way I thought of it in the first instance, but there is a way to explain this using transformation optics. So the way I think of this lens is as this is a piece of negative space. Now I'm going to show you how you can make a piece of negative space by folding space. So here's a bit of space which is just ordinary space. And you remember that slide a little time back where I compressed the region of space. So I'm going to compress this middle region of space here. And I increase epsilon mu and I decrease epsilon mu in these two orthogonal directions. And the more I compress, the more extreme these values become. And eventually I get to this situation here where I've infinitely compressed. And you know what happens to when you go through a singularity, you have a function which is, let's say, 1 upon x, and 1 upon x is positive when x is positive, and as x goes through 0, 1 upon x goes to infinity, and then it emerges the other side as a very large negative number. And that's exactly what happens here. So if you can compress space more than infinity, I'm a theorist, I can do that, then you get this bit of space here, which has been folded back on itself. And you apply my formula for compression of space, and you find that this bit of space here, which had been ultra compressed, has a negative refractive index because you've made both epsilon and mu negative. And what you see is that you've actually made a very, very curious bit of space. And it's curious because you've bent space back on itself. Now, you've heard people talk of parallel universes, and here you don't have a parallel universe. It's one manifold on which you and I exist. But here, if you could do this, you've actually bent space back on itself. So in this region here, there's not one manifold, but 3 manifolds. So if you pass this point, if light passes this point and sees an object here, it will then be turned back on itself, and it will see the object a second time. And then, as it emerges from this negative refracting region, a third time. Okay, so I mentioned when I first introduced negative refractive index and the waves going backwards, it's a bit like moving the clock backwards. What it's more like actually is moving space backwards. Now, you can understand from this that if you believe this picture of generating negative refraction from folding space, that you can understand how the lens might focus something once, twice, and 3 times. 3 foci in this. Furthermore, this theory of transformation optics is valid not just for rays, but it's valid for all waves, whether they be evanescent or whatever, because it's exact to the level of Maxwell's equations. And therefore, this image should be perfect in all respects, providing you can make some space with this property of exactly a negative refractive index. And then you will think the light is doing this, but what the light thinks it's doing is going around in this curve here. Now, there are some experimental realizations of that, but I do want to get onto the modern applications. So I'll just, well, yeah, I think actually, so I'm going to finish on time. Manoj, you want me to finish on the hour, do you? Is that correct?
Yes, sir. You have around 15 minutes more. I mean, 10 to 15 minutes.
I have 15 minutes more.
Yeah.
Okay, because I reckon I have 7. If I have 15 minutes more, that's great, because I can tell you this story.
Sure. Sure.
Okay, so here's the ideal formula for negative refractive index. Is that epsilon and mu are both negative. And that's essential because light consists of an electromagnetic wave, electric and magnetic fields. But suppose we have an image which is very, very small, an object which is very, very small. Suppose you're trying to look at a molecule which is maybe a nanometer, 10 nanometers across, and that's emitting light. That's much less than the wavelength. Now, when light starts off from the molecule, it's usually an electrical transition that is responsible. And light is like a dance. So it starts off from the molecule as an electric field, and then half a wavelength later, it turns into a magnetic field. And then another half wavelength electric field. So it's dancing around between electricity and magnetism. But if everything you're looking at is on a very small length scale, much less than the wavelength, then the electric field, which is the light starting off from the molecule, never has a chance really to acquire much magnetism. And so for really, really small objects, we really don't care about mu, because there's no magnetic field for it to act upon. And this was the basis for my proposing a poor man's super lens, which has only epsilon negative. And that can be realized relatively simply because there are materials such as silver, which in the visible region has a negative epsilon, but a positive mu. And that was exploited by Zhang's group at University of California, Berkeley. And they constructed this setup here. So what they have here is something to look at, which is a chromium, very, very thin chromium layer, 50 nanometers thick. And onto that, they etched a grating, which was 60 nanometers period, I think, and the word nano here. And then they put a spacer layer and a layer of silver, tune with the frequency tuned so that the refractive index of this, the epsilon of this was the negative of the ppma. And on top, because you can't see an image which is smaller than the wavelength of light, they put a photoresist. And the way they saw the image was to strip the photoresist off and to look at that under an atomic force microscope. So here we are, this grating here has a 60 nanometer period, and with light, which is has a wavelength 6 times larger than this, you're seeing this sub-wavelength image. Perhaps more impressive is this picture here, where you have a focused ion beam image of the object, the word nano, and then atomic force microscope. So if you miss out the silver, then of course you don't do any focusing, and you get this rather coarse image of the word nano, and the half width of these lines in the letters is 221 nanometers, comparable with the wavelength of light being used. But if you put the silver lens in place, you immediately, it's like popping your specs on, you immediately get this much sharper line here. So that was the, not the first, but the first at visible frequency demonstration of super resolution. And now I want to come to, having gone through all the theoretical and early experimental background, I want to come to what's happening recently. So lots of applications. One of the first companies to get into this was Kymeta. And it turns out that you can make quite a good satellite communications receiver and transmitter using metamaterials. So traditionally, if you work in remote location and you're a journalist, you have to communicate with your base station, you use a sat-nav phone, and that consists either of a steerable dish, which is about 30 centimeters in diameter. It's heavy, it's expensive, it takes a lot of power. Or if you work for a very wealthy company, you take a phased array, which is a mass of silicon electronics, and it's lighter and it's flat. It takes quite a bit of power, and it's very, very expensive compared with the dish. You can, in fact, make a phased array out of metamaterials using the ability to tune their properties just by applying electrical potentials to the split rings on a suitable substrate. And this has now been commercialized and is available for sale. Another company which has used this related technologies, now not at satellite communications frequencies, but at terahertz. And the idea here is for security at airports. So at the moment, if you go through a terahertz scanner at the airport, you may have been through these, you have to put your arms up. This is a big cylindrical machine, two rods circulate you, and several minutes later, you're passed and there they go through. How much more convenient is, as you walk to check-in, a terahertz directed beam could scan you and do that check whilst you're on the move. And the company called Evolve, which is related to the mother company, Intellectual Ventures, which also spun out Chi-Meta. This figure is out of date. Bill Gates has now chipped in 50 million, I believe. And this is now commercially available. My colleague Richard Sims is working with improving MRI. Magnetic resonance imaging picks up the very, very weak magnetic signal from a rotating spin in an atom or molecule, and then uses that to sense the environment of that spin and get MRI images. And MRI is a great technique because it's totally non-invasive, and it can spot things like prostate cancer that other techniques, imaging techniques, can't see. And one of its applications is to look at the heart. And there you need a very, very fine resolution scan to see defects in the heart. And so the pickup coil, which senses these very tiny magnetic fluctuations, has to be put inside the heart. And the way they do this is to cut a vein in your leg, shove an electrical coil up that vein until it reaches the heart, and then do the experiment and scan the heart. Now, there are a few problems with that, because in a magnetic resonance setup, there are all sorts of very powerful fields around, some of which can couple to that copper wire you just put in somebody's vein. And if it gets hot, that's really bad news, because it sticks to the side of the vein. And so some care has to be exercised. So Richard asked the question, why is it sensible to take this deliciously weak and fragile magnetic signal and turn it into an electrical signal? Why do you have to do that? And it's counterintuitive, really, because one of the problems with a very weak signal is that you're very vulnerable to noise, and the body is electrically very, very noisy. There's a theorem which states that if you have a resistive material, and flesh and blood and so on are quite resistive, then they are also going to be electrically very, very noisy. However, the body has virtually no magnetic response, a little bit in the blood because of hemoglobin, but not much. And so the body is very, very quiet for magnetism, which is why you can pick up this very weak signal. If it were an electrical signal, you'd have no chance. But why turn this lovely magnetic signal into an electrical one? Why not keep it as a magnetic signal? And using metamaterials, Richard was able to do that. And he's now in the business of commercializing this. I did mention that the concept of changing something's properties by altering its structure was not now confined to electromagnetism. And Ping Sheng, who works at the Hong Kong University of Science and Technology and is a very distinguished theorist working in acoustics, has come up with this idea that you could make a screen that was prevented sound transmitting through it. Now, if you're an architect designing apartments and you wish to have them acoustically insulated so that neighbors don't annoy one another, then your problem is that although walls are very good at keeping out high frequency sound, so you can't hear the next door neighbor's budgerigard, or if the child plays the violin, then you can't hear the violin. If your next door neighbor plays the drums and you have very low frequency sounds, they get through walls quite easily. And so low frequency sounds are a real problem. And there's a rule in architectural engineering that says if you wish to keep out a low frequency sound, then you have to have a very thick, heavy wall. However, that is not the only way of doing it theoretically. Theoretically, sound waves obey second-order differential equations, and there are two boundary conditions which can reflect the waves and stop them going through an object. One is the architect's chosen one, which is to have a very, very heavy wall, which essentially cannot be displaced by the sound and therefore doesn't transmit the sound. The other is to have an infinitely light wall, which cannot transmit pressure. So if you transmit the displacement, you transmit the sound. If you don't transmit the sound. If you transmit the pressure, then you also transmit the sound. But if you cut the pressure translation off, then, but the problem is finding something which is infinitely compressible. Metamaterials to the rescue. Here are a series of resonators for demonstration purposes placed in a tube, and Ping has demonstrated that this very light array of resonators can completely prevent sound, low frequency sound, from being transmitted. And this is now being commercialized, so you could now design large screens, several square meters in size, which will effectively screen an area from sound. That's thanks to metamaterials. Perhaps the most exotic example was produced by a former postdoc of mine, who's one of the most imaginative guys I've ever seen. Sometimes he's a bit off spectrum, but this is Sebastian Gueno, and he said, well, earthquakes are waves. We'd like to stop them. Can we do this with metamaterials? And here's an experiment he persuaded an oil company to do. This is a site near Marseille, and they've drilled some holes into the ground. So they've made a metamaterial out of the ground, and then they go around with this thing which is called a thumper trap, and essentially it lifts a heavy weight and it drops that onto the earth to simulate an earthquake. And then they see a detector here how this earthquake wave has been deflected by this array of metamaterials. Well, you know, you're not going to drill holes around the Empire State Building in New York, but you might want to drill them around a nuclear power station. Think of Fukushima. The most recent advances in metamaterials have to do with not only structuring the material in time, in space, but to structure it in time as well. Now, this is very difficult because materials don't like to be changed very rapidly in time, and it has to be very rapid to have an effect. But there are possibilities emerging. Here's a multi-author paper. You can see how many people are interested in it. That's our own Ricardo Sapienza there from Imperial. And they have developed a system exploiting the fact that epsilon near zero materials, such as graphene, can be modulated at very, very high frequencies. And so you can have this interaction of a time varying system with light, and that really has some fascinating consequences that theorists are only just beginning to explore. Here's another one. This is Federico Capasso, who works at Harvard. He's a guy I mentioned earlier in connection with quantum cascade lasers for terahertz, but here he's doing an optical experiment. And he is designing a very, very thin lens, which is only a few nanometers thick and consists of some background layer onto which he's put these metallic structures. And the idea is that each region, because of its different shape and orientation, each region responds to light, refracting the light with a different phase. And so you can make a lens that can do all sorts of extraordinary things, and a lens which is very, very thin. And you might imagine that people might be interested in that for sensors. So that's a very quick run through. I think I'm out of time, so let me summarize. We've opened new materials with our materials for making materials with properties impossible to achieve with naturally occurring materials. With them, we control light on all length scales down to a few nanometers. They've been used to deliver mobile phone antenna for 5G. We're working on sub-wavelength microscopy. We've not achieved a practical system yet, but we're working on it for biological applications, and that's being developed in University of California, San Diego. Cheap and efficient control of terahertz radiation, as in collision avoidance in automobiles, and also at low frequencies in satellite antennae. Safe delivery of MRI signals, classified military applications that I know exist, but I'm not personally involved with. So that's the end of my talk, and thank you very much for inviting me and for your attention.
Thank you very much, Professor Pendry, for enlightening all of us, and especially this 50-year journey in a small time frame of 60 minutes. That's really commendable. Okay, so there are a few questions which are there in the chat section. Would you like me to take up those questions, or you would like to see those questions?
I think it would be most productive if you read them out, and then we could all hear them, and I would hear them clearly.
Fine, sir, no problem. Okay, so the first question is whether the materials with negative refractive index, they have negative temperature coefficient also.
Not necessarily. They may have, but most of them that have been made don't have. No.
Okay. Okay. So, sir, what is the thermal coefficient of the metamaterials in comparison to like any other material?
The thermal coefficient. Well, they can have thermal properties. I'm not sure what you mean by the thermal coefficient, but let me try and give you an example of thermal property. So one thing you may want to do is to construct something which absorbs heat very efficiently, okay? And to do that, you can design a structured surface which will absorb infrared light. And in fact, very, very fine particles of gold and silver, I mentioned before, and platinum will, when they're structured as very fine particles, will be very efficient absorbers of radiation. And you may want to do that because when you're sensing heat, thermal radiation, you do it through a bolometer, and you want that bolometer to absorb the radiation very efficiently. But at the same time, you want the bolometer to have a very low thermal capacity. And so you want an efficient absorber which can be very thin and light. And the gold blacks and the platinum blacks do that. There's another application, though, to heat, which Martin Wegener has in Karlsruhe has proposed, and that is to say that recognize that just like light, the heat diffusion equation can be subjected to this transformation optics treatment. And he has designed a cloak which will direct the flow of heat away from a given area. So you can control heat with metamaterials by structuring them so that they can make the heat flow in the direction you want. So yes, there are applications to heat flow.
Okay, I'll take up the next one. This is by Sayak Bhattacharya. Is just a comment and then followed by a question. The light travels a different distance through different refractive indices in the cloaking medium. Then it would have if there was no object present in the path of light. Essentially, this changes the phase of light. So if someone does a phase contrast imaging, he or she can detect the presence of the object.
No is the answer, but that there is another hassle which I'll mention in a moment. The cloak attends to the phases all correctly, because it deals with the fields and not with the, but it does so only upon frequency. Now, if you really wanted to detect that there was a cloak there, you'd exploit the fact that the metamaterials you have to use in a cloak, it turns out that their response has to depend on frequency, not drastically, because you can make quite effective cloaks which operate over a range of frequencies, but they do have to depend on frequency. So although the phasers may be absolutely correct at one frequency, if you look at the cloak with a different color of light, you would see small differences, and so you could detect through the change of phase that there was something there. So yes, it has to be a black and white cloak, I've heard, or red and black cloak.
Okay. So there's another question, sir. The unit cell of the metamaterial consists of metals, which is typically lossy at the optical frequencies. How challenging would it be to realize lossless materials at visible frequencies?
Yeah, that's absolutely right. At optical frequencies, you have a big problem if you want to design things with metals in them. They are lossy, and it turns out that loss, particularly with the lens, is what limits how perfectly so-called perfect lens can focus. If it's lossy, it doesn't focus quite so well. There are ways forward, because for many applications, you do not need the extreme responses that metals give. The advantage of metal is that they have an absolutely enormous conductivity compared to an insulator, and so you get huge contrasts. But people are increasingly interested in dielectric metamaterials, simply because dielectrics can be found with very, very low losses. And so although in terms of contrast, they're not quite so effective with metals, and therefore the structures have to be slightly bigger, people are now moving on to make dielectric metamaterials.
Okay. There are three more questions, sir. I'll take up the next one. If some applications need epsilon or permeability as continuous function, which it may not be possible with ordinary materials, so is it anyhow possible with the metamaterials to have or to realize continuous epsilon or permeability function?
The answer is yes, but qualified, because the metamaterials consist of a sub-wavelength unit cell, and on a scale greater than that structure, you can make them continuous. So, for example, if you could probably see that, so I'll take that off. If I go back to this slide here with from Capasso's group, what Capasso here is doing is trying to make a continuous variation of essentially the refractive index of the lens by varying continuously the shape of the metamaterial elements. But of course, because it's discrete, there are discontinuities across the boundary here, and the idea is that if the wavelength is long enough, then it doesn't see those discontinuities.
Okay. I'll take up the second last question now. The Veselago lensing effect has been observed with two-dimensional crystals possessing the Dirac points. Can you please explain this?
I've not seen that application. That's an interesting idea. I never thought of using them like that. Maybe the questioner should do the experiment. That would be nice.
Okay. Okay.
Sorry, I don't know.
Sure, sure. Okay, sir. I'll take up the last one then. What are active metamaterials?
Actually, metamaterials are metamaterials that can be whose properties can be altered in real time. And the way you do this is, if I could go back to one of these early structures here. So now, if you look at these split rings here, if you make this substrate a material that changes its dielectric function as a function of the voltage applied to it. So you apply a charge to this ring, a DC, quasi-static charge, for example, then it would alter the permittivity of the substrate, and that would alter the resonant frequency of this ring. And this effect is used to tune the response of metamaterials. So very, very cheaply, all you need is a substrate that RF responds to an electric field by changing its permittivity. And very, very cheaply, you can tune the property of this ring. So just with an electrical contact and a dirt cheap substrate, you could make something which, for example, in a phased array, will be done with very expensive silicon. And that's why these phased arrays that you can make with metamaterials are so cheap and will be quite ubiquitous in the near future, I think.
Okay. Thank you very much, sir, for taking up all possible questions. And although I planned the seminar to be for about 60 minutes, but looking at the questions and the inquisitiveness of the audience, I think that we have overshot the time by about 20 minutes or so. But
I'm sorry.
no problem, sir. But I must appreciate all the attendees, especially today is a holiday, a big day for all Indians. But despite of that fact that they have spent nearly 90 minutes being there to listen to you, and a big thanks to you, sir, also for taking out your precious time and enlightening all of us. So on behalf of the NASI Delhi chapter and the host institution, I would like to thank you as well as to all the attendees out there, sir.
Thank you very much, and congratulations on your Independence Day.
Sure. Thank you very much, sir. Okay. I just seek your permission to close the session for now, sir.
Yeah.
Sure. Thank you.